Welcome back, folks. Day 3 of our conference, and it's a great pleasure to introduce our first speaker of the day, Taichi Uemura of the University of Amsterdam, who will speak about abstract type theories for those of us who are really tired of this concrete, boring type theories.
Okay, thank you very much. Thank you for organizing this conference, and thank you for inviting me for a talk. So today I talk about, well, as the title suggests, type theories, which is kind of abstractly defined. So the goal of this talk is very simple: to define a general notion of a type theory and give a unified account of semantics of type theories. So in a sense, the topic of this talk is much similar to Peter Ramstein's talk on Monday, but I mainly focus on the semantic side of type theories rather than syntax of type theory. And the main difference between Peter's approach and my approach to general notion of a type theory is that I define a type theory to be a mathematical structure rather than a set of inference rules. And so in this sense, I regard inference rules as a presentation of a type theory. But I think a type theory should be something else presented by a set of inference rules. So I think this makes, to some extent, so my definition of a type theory will make it easier to study some aspects of type theories, because type theories will become just a mathematical structures rather than a complicated set of inference rules. So, but the thing is, this is too, in some sense, my definition of a type theory can be too simplified, oversimplified, so that I lose some information about type theories, like computational aspects, which is very syntactic. So I think I cannot discuss much detail of the syntax of type theories. But as long as we are interested in semantics of type theory, I believe my approach is very, I don't know, at least I can make the theory of semantics of type theory very simple, right? Okay. So before proceeding my talk, I have to make some limitation on the scope of my framework. So in this talk, type theories I have in mind is like kind of a Martin-Lev type theory, the book code, two-level type theory, some CCHM cubical type theory, and so on. These type theories have some common properties. One of these is every context in this type theory is single layered, which means single layered. So an example is a spatial type theory of Sherman, in which context are split into 2 layers. And also, and also index type theory from the yesterday's talk has also context in 2 layers. So, but I cannot I don't. But such type theories are out of scope. And also, the second important property is these type theories. In these type theories, everything is stable under changeable context. Or in other words, everything is stable under substitution. Okay. So roughly, our type theories are basically type theories with semantics based on categories with families. Okay. Okay, so there are some important concepts around the semantics of type theory. So one important concept is, of course, type theory, because it is the study of type theory. So type theory is intuitively a formal system presented by a set of inference rules. And for each type theory, there should be a notion of a model of a type theory, which is a mathematical structure that can interpret the inference rules. And type theory is also a kind of language for doing mathematics. So in that sense, I can write some theory in some type theory, so which I call a theory over type theory. Yeah, I know this is very confusing terminology, but well, it is something called theory, like algebraic theory or first order theory and so on, which means that it is something presented by a set of type symbols, term symbols, or predicate symbols and axioms. And and in this talk, I mainly focus on one of the aspects of the semantics of type theory, which is sometimes called theory model correspondence. Yes. I mean, so given a type theory T, I can make a category of theories. Given a type theory T, we have a correspondence between theories of a T and models of T. And precisely from a theory of a T, we can build a syntactic model. And conversely, from a model of T, we can form a theory of a T called the internal language of the model. And they are often in a junction and sometimes in equivalence. So I think this is a really important step in the semantics of type theory. Okay. And so typical example of type theory is basic dependent type theory, which is just a dependent type theory without any type constructors. So the only inference rules of this type theory are the structural rules of weakening, projection, and substitution. Okay. And then model of the basic dependent type theory is a category with families. Yeah, actually there can be several notions of a model of dependent type theory. And one of such notion is a category with families. And then a theory of dependent type theory is nothing but a generalized algebraic theory. And example of GAT is the theory of a category, which consists of two type symbols of objects and morphisms, and two term symbols of identity and competition, and three axioms for as usual. Okay. And then I have a correspondence between GAT and CwF. From given a GAT, I can form a category of context and context morphisms, which is equipped with the structure of CwF. And from a CwF, if we collect types and terms in the CwF, we get some theory, generalized algebraic theory, which should be called the internal language of CwF. Okay. So this is a typical example of my framework. Okay. So here is a to-do list in my talk. I will define notion of a type theory, and then a model of a type theory, and a theory over a type theory, and then establish a theory model correspondence. And more precisely, the semantics I will develop is functorial semantics of type theories, which means that the type theory is defined to be a category equipped with certain structures. And the model of a type theory T is then a structure preserving functor from T to presheaf category. Theory of a T is a little technical, so I'll explain later. And then, well, so the theory model correspondence is constructed and proved in a purely categorical way. It's a very nice. Okay. Any questions at this moment? Okay. So here is an outline of this talk. So, so the goal was to define a general notion of a type theory. And to do this, I first look at models of a type theory, like CwF or and so on, and guess what a type theory should be. And then, once I define the notion of a type theory, then a notion of model will be straightforward. And then I look at what a theory of a type theory is. And then finally, I guess I quickly explain my main result. Okay, so let's begin with models of a type theory. So our notion of a model I have in mind is basically model based on categories with families. But I mainly work with alternative formulation introduced by Steve Audi, which is called a natural model. So I review the theory of natural models. So a natural model is a category C with a terminal object together with a map of presheaves over C and D from E to U, which is required to be representable in a sense that given a map from a representable presheaf to U, then the pullback of this the pullback of E along A is representable. In other words, given such a map A from representable to U, then we obtain object brace A in the base category and the pullback in this form. Okay. So what does it mean? So basically, object in the base category is thought of as a context in type theory. Then a map into U is a kind of a type over the context gamma. And in this interpretation, the object brace A is thought of as a context obtained from gamma by extended by A. Then so these two maps are kind of projections. So in this way, natural model has enough structures to interpret basic structure rules of dependent type theory. Okay, and this definition is really, and the natural model is really equivalent to a category with families. Okay. So a natural models basic structure rules. Then what about type constructors? Well, type constructors are usually basically modeled by maps between presheafs. For example, consider the extensional identity types, which will be modeled by pullback in this form. So the lower and the bottom map correspond to type formation rule for identity types, and the upper map is the constructor. And being a pullback means that this identity type is extensional. Okay, so this is okay, but what about the pi types? Yeah, pi types are a little complicated because pi types bind some variable, so it's not obvious. So to model variable binding, yeah, we use the polynomial functors. So let me see. So let D. Sorry. Okay, so in a presheaf category, any pullback functor has a right adjoint called push forward. This is nice. And then using this such a push forward, we can define a polynomial functor P of D, which is defined as follows. But the only important thing in this definition is that we use the push forward along D in the definition of the polynomial functor. Okay, the other is just a finite limits or just a four-vector functor. And in a special case, when D is a representative map of presheafs, then this polynomial functor classifies some kind of families, which means that if for any presheaf X section of this object, the presheaf EDX are equivalent to the pair of sections A and X, in which A is a section of U. So I think of A as a type over gamma, and X is a family section of X over the context comprehension of A. So in this sense, the elements of P of X is a kind of family of elements of X indexed over some type. So in other words, well, P of X PDX classifies a family of elements of X. So in particular, PD of U classifies families of types, and PDE classifies families of terms. Okay. So using this polynomial functor, I can define, say, pi type structure. So pi type should be modeled by a pullback in this form. So pi is just a formation. Pi corresponds to the formation rule for pi types, and lambda is a constructor for pi types. And being a pullback means that the elements of pi types is basically the section of the second argument. Okay. Okay, so in this, at this moment, we have some notions, some important concepts around natural models, namely representable maps, finite limits, and push forwards around representable maps. I mean, so representable maps is important. Of course, a natural model is a representable map, and I use the finite limits to model certain type constructors. And I use push forwards along a representable map for modeling variable binding. So these three are, I think, important concepts around natural models. And in other words, I can regard a natural model as a diagram in the presheaf category, written in the language of these concepts. So the idea is that and my idea is that because the natural model is a diagram in a presheaf category, so it is a functor from some category to a presheaf category. That's the idea. So the idea is very simple. Because natural model is a diagram in a presheaf category, so it is a functor. Okay. So to make it precise, I introduced such a category equipped with these structures, and I call it a category with representable maps. As I promised, it consists of a category C and a class of maps called representable maps. And I require C to have finite limits and push further along representable maps. Okay, that's it. A typical example is, of course, a presheaf category with representable maps of presheafs. Okay. Then I just define a type theory to be a small category with representable maps. Yeah, the smallness is just a technical convention. And model of T is consists of a category, the base category M star is a terminal object, and the structure preserving functor from T to the presheafs of M star. Okay. So it's very simple. And okay, so I defined the notion of a type theory, so I guess I should give some examples. But I'm sorry, these examples are a bit abstract. I define, so I consider the basic dependent type theory. So I define the basic dependent type theory as a category with representable maps freely generated by a single representable map. Yeah, so from the definition of a category with representable maps, this definition is a kind of algebraic thing, some category and class of maps, and finite limits and push forwards are right adjoints, so it's a algebraic in some sense. So we can such a kind of free representative map category exists. And anyway, so this makes sense. So I define, that is, I define the basic dependent type theory to be the type theory freely generated by a single representative map D from E to U. And freely generated by this thing means that the following universal property, the morphisms from G to some other category with representable maps are equivalent to the representable maps in the codomain. So from this universal property, a model of G is precisely a category M star with a terminal object together with a representable map of presheafs of M star. This is precisely a natural model. Okay. So this G is just a type theory whose models are natural models. Okay, and how to adjoin type constructors. Again, I use some free construction. I define a type theory with pi types, which I denote G pi to be the type theory freely generated by a representative map D and a pullback in this form. So a model of G is just a natural model together with a pi-type structure. Okay. So what? Okay. So, but how to define more complicated type theories like cubical type theory? And so in this definition of G and G pi, I just follow a general principle for encoding a set of inference rules as a category with representative maps. I mean, so consider that given a set of inference rules, how to define a category with representative maps corresponding to such inference rules. So in general, I use some free constructions. And the strategies, the most important principle is basically I represent inference rules as morphisms in a category with representative maps. So for instance, I adjoin to G pi a morphism pi like this. And this is because G pi should have inference rule for the pi formation rule. So this morphism pi is represent this inference rule pi types. So then what is the domain of codomain of morphisms in category with representative maps? I think it's this objects in the category with representative maps should be called judgment forms. So for instance, the object U in the basic dependent type theory corresponding to the judgment form, something is a type. Okay, and so okay, and morphism in a type a category with representative maps represents inference rule and inference rule. But at the same time, I can regard a morphism in a category as an object in the slice category. And in that case, I can think of such a morphism as a family of judgment forms. So for instance, the object E, which I regard as an object in the this slice category, it represents a family of judgment forms. Something is an element of a type. And then when I make morphism representable, basically when judgments of the type theory can have hypotheses in this form. So for instance, the morphism D in the basic dependent type theory should be representable because judgments in dependent type theory can have hypotheses in this form. But the map from U to the terminal object should not be representable because judgments in DDT cannot have hypotheses in the form of X colon type. Okay, so this is a kind of general strategy for encoding type theory into a category with representable maps. So basic strategies I represent inference rules as morphisms, and judgment forms as objects, and make morphisms representable if judgments in this type theory can have some hypotheses in such a form. Okay, so following this strategy, we can define cubical type theory to be the category with representative maps freely generated by something. One of some things is Also, cubical type theory is an extension of dependent type theory, so it should have a representative map corresponding to judgments from type and something is an element. And also, cubical type theory has another sort of judgment. Something is a cofibrant proposition, and something and a cofibrant proposition is true. So corresponding to these judgment forms, I have joined another representative map like this. And because cofibrant propositions are propositions, I make it kind of map from the kind of monomorphisms, and it turns out that the domain should be its terminal object. Anyway. And another feature of cubical type theory is that it has the unit interval. So I would add an object I, and the map from I to some object should be representable because everything in cubical type theory can depend on the unit interval. So it should be representable. And then the morphisms corresponding to inference rules, then I get something. I get some type theory corresponding to cubical type theory. Okay. Anyway. So some summary for models of type theories. I define the type theory to be a category with representative maps, finite limits, specifiers, and representative maps. And the model of type theory is just a structure preserving a functor into a presheaf category. And with this simple definition, we can actually define a wide variety of type theories using certain free constructions. Okay. So I have done the first two items. I defined the type theory and the model of type theory. And the rest is to define a theory of a type theory and then build a theory model correspondence. Any questions at this moment? Around this. Okay, good. So then I look at theories of a type theory. So what is a theory? Informally, a theory is something presented by type symbols, some symbols and axioms. Okay, so like algebraic theories, first order theories, generalized algebraic theories, all kinds of theories are presented by symbols and axioms. But it's not. But again, these symbols and axioms are just a presentation of something else. And what is something? What is this something? So yeah, as the frame title suggests, something should be an algebra. Precisely, by an algebra, I mean a model of an essentially algebraic theory. So given a set of symbols and axioms, then the sets of types and terms generated by these symbols and axioms and the type constructors of T will form a kind of algebra. And I use an algebra in some generalized sense. It means that these algebra can be many sorted, and operators between these sets can be partial operators. So precisely, it is a model of an essential algebraic theory. So, for example, given a generalized algebraic theory, we can form the set Un of types of a context of length n, and the set En of terms of context of length n. And we have partial operators between these sets Uns and Ens defined by the structure rules of, say, weakening and substitution. So, in other words, a generalized algebraic theory presents an algebra whose carrying sets are the sets of types and terms. And there is a much more strong result, which asserts that generalized algebraic theories can be identified with such algebras of types and terms. Okay. Okay. But this statement is not precise, but essentially, in so Richard Garner proved that the category of generalized algebraic theories is monadic over some presheaf category, but which means that the category of GAT is equivalent to some category of algebras, and whose underlying sets are precisely UNs and ENs. So, okay, and from this, under this identification, it is natural to define a theory over T to be an algebra of types and terms. But it's still informal because I don't give I don't give a description of an algebra of types and terms. And I also note that such kind of definition, I mean theories as algebras, coincide with, agree with some algebraic approaches to dependent type theories like B systems of Webowski, and also there is a paper by Isaev on algebraic presentation of dependent type theory. So yeah, in these papers are basically these papers basically says that theories can be identified with algebras. Okay. Okay, so but okay. So by the way, in general, algebras can be identified with left exact functors, which follows from the theory of locally presentable categories. So precisely given category of algebras and their homomorphisms, then such a category C is always locally finitely presentable, which implies that there exists, we can find a small category sigma with finite limits, such that C is equivalent to the category of functors preserving finite limits to the set. Okay, so in that sense, basically algebras are left exact functors. I mean, left exact functor is just a functor preserving finite limits. So because okay, so what should we do? A theory over type theory was a set of presented by symbols and terms. simple transactions. And the theory of type theory was identified with an algebra of types and terms. But now an algebra is identified with a left exact functor. So so all we have to do is to determine the domain of such a left exact functor. So that given a type theory T, I define the suitable category sigma T with finite limits, so that I can define a theory of a T to be a functor to set preserving finite limits. Okay. Yeah, but in fact, we can simply put sigma T to be just T itself, because the type theory T is defined to be a category with representable maps, and I require for it to have finite limits. So T itself is a finitely complete category, and I have a result. For example, in the special case when T is a basic dependent type theory G, then there exists an equivalence of the category of GATs and left exact functors from G to set. So I only explain the one. I only explain the construction from the right to left. So given functor k from G to set preserving finite limits, then we obtain algebra of types and terms described in Garner's paper. Sorry, that's previously. So because G contains representative map D, so we can form a polynomial functor P of D, and this object is a kind of, and this set is a kind of set of types, and this set is a kind of set of terms, and then we have some kind of we have other operators between these sets, and so it forms an algebra of types and terms, which is equivalent to generalized algebraic theory. And with much more effort, this construction is in fact an equivalence. Okay. Yeah. So anyway, okay, so from this result, I can simply define a theory over a type theory T to be a functor from T to set only preserving finite limits. Okay, so to summarize, type theory is a category with representable maps, and the model of T is a structure preserving functor to a presheaf category, and the theory of T is a functor to set only preserving finite limits. Okay. Any questions at this moment? Okay, good. So I have defined the type theory, model of a type theory, theory of a type theory. Okay, so I explain my first result around this concept, kind of theory model correspondence. Okay, a general picture is like this, where T is a type theory. Then we form a category of theories of T and category of models of T. and define a junction like this. The right adjoint is assigns the internal language, and the left adjoint assigns the syntactic model. And all these constructions and proofs are really category theoretic. Okay, so for instance, look at the internal language. It's very simple. Given the model of type theory T, which is just a structure preserving functor from T to some presheaf category. And I require, and the presheaf category, the base category M star is required to have a terminal object. So I have the variation functor at terminal object. And I define the internal language of M to be this composite. And this defines a functor from models of T to series of T. So first, the first result is this functor L from models of T to series of T has a left adjoint, and moreover, the left adjoint is free faithful. Okay. The proof is a kind of adjoint functor theorem. So, okay, and so because the left adjoint is free faithful, it's natural to ask what is the essential image of the left adjoint. And I can show that it is the class of democratic models, which is a democratic model is a model of a type theory T, in which every object in the base category is reachable from the terminal object by finitely many context extensions, basically. And yeah, and as I said, the essential image of the syntactic model functor is precisely the class of democratic models. So you get you get an equivalence of democratic models of T and series of T. It's nice. I don't know. This is a second main result, and that's so I guess we have done. I defined a type theory to be a category with representable maps, and the model of type theory is a structure preserving functor to a presheaf category. And the theory of a type theory is a functor to set preserving only finite limits. And the theory model correspondence is a kind of a joint functor theorem. Okay, so finally, let me advertise my current project with Huang Yuan. Yeah, so I defined the type theory to be just a category with structures, which suggests that I can generalize it to an infinity category with representable maps. And I get similar result and something interesting. And I can find some interesting infinity type theories, like infinity type theories, which is kind of internal language of left exact infinity categories. And also we find infinity type theory, which is an internal language for locally partition cross infinity categories, and so on. I think this is this project is a really interesting future direction of this framework. Okay, yeah, I think this is the end of my talk. Thank you very much.
All right, thank you so much. So we're going to start with silent applause. So please join me in thanking Taichi for this talk. And I shall open the floor for questions, comments, and other remarks. of the kind that you may desire. Maybe I'll start then, since I didn't give anyone time to volunteer. So can you say a bit more about what's more? So in particular, there's a natural, on this slide, there's a natural third row to have there with elementary infinity duplexes. I was wondering
if you... yeah, it's under construction.
I mean, what's under construction? As in
yeah, of course. Yeah, the definition of an elementary infinity tuple is, I think, under development, I guess. And also to define what infinity type theory corresponding to elementary infinity tuples is so it should be an infinity type theory with I don't know, all type constructors that homotopy type theory has. But for instance, higher inductive types. So how to define higher inductive types in my definition of a type theory is even not clear. Yeah, so this and more part is actually under construction.
Okay. So I occasionally find myself surprised to learn that there are other people than me, so I'll let them ask questions as well. Feel free to unmute your microphone and ask the question, or you can type it in chat, and my limited reading abilities should be put to use.
Well, I'm also very interested about that last slide that Chris asked about. Can you just say another word or two about what an infinity type theory is and whether it's something that can be worked with in practice, like presented in some finitary way or something like that?
Yeah, informally, well, infinity type theory is a kind of type theory in which judgmental equalities are replaced by a kind of homotopy. But okay. Yeah, so in my definition of a type theory, which is a category with representative maps, in which judgmental equalities are kind of defined by equalizers of some morphisms. But in infinity type theory, equalizers are of course replaced by homotopy equalizer. So judgmental equality becomes a kind of homotopy.
Thank you.
So perhaps this is maybe Dan's question again, but phrased from a different angle. That I'm also interested in the sketch definition of infinity category. That one of the things that's kind of is the direction we came from in our definition of type theory, and that your main general definition of type theory also excellently satisfies, is that it's something that you can have a syntactic formal system that you can work in. And your main definition of the categories of the representative maps beautifully satisfies this. And then do the infinity type theories also satisfy this? Can you write down a system to work internally in them in a syntactic way?
Well,
or for certain presentations?
It's future work. I mean, it's not obvious what is the syntax for infinity type theories.
Right, but your expectation would be that they would have a syntactic way one can work in them?
Yeah, I hope. I hope that there should be a syntax some kind.
Okay.
Okay, more questions? Okay, so someone unmuting their microphone as Peter was asking a question.
I have a question.
So, oh, yes.
So you showed us how the basic dependent type theory and cubical type theory can be seen as more representable map categories. Can you also describe cubical type theory as a theory in your sense over basic dependent type theory, for example?
No.
So they're like
no, I guess.
they're like orthogonal kind of type theories.
Sorry.
They're like orthogonal kind of type theories. It's not like one is an extension of the other in your setting.
What do you mean by orthogonal?
I mean that's can you I guess the I don't know, I understand the notion of a theory over a type theory as a way to extend the type theory with more
okay.
constructors or more types.
Well, but a theory of a type theory is as I said, it is sort of as an extension of the base type theory, but this extension is only, let's say, this extension is only obtained by only adjoining type symbols and axioms, but no inference rules.
Okay.
So in that sense, so cubical type theory has a more inference rules than basic type dependent type theory. So in that sense, I think cubical type theory is not written as a theory of the basic dependent type theory.
Okay, thank you.
And may I just comment on that question? Am I understanding right that part of what makes the cubical type theory not a theory over the basic one is that it has not just more constructors and things, but more judgment forms specifically, right?
Yeah.
And so that's what goes beyond what a theory over the basic one could cover.
Right.
But I assume there is some kind of functor between the category that presents ordinary dependent type theory or homotopy type theory and the category that presents cubical type theory. There's probably some relationship that you could, pull back along or something like that. Is that right? Is there some kind of functor between the category that defines, say, dependent type theory and the category that defines cubical type theory?
Yeah, of course, there is an embedding from the basic dependent type theory to cubical type theory.
Right. So there's an extension of in that sense. In a slightly
in that sense. In that sense, yeah. Right.
Okay. We have a question in the chat. So maybe I'll just jump to the question. So maybe you said it already, but is there a notion of a model for a theory over the type theory? So.
There can be. There can be, but it is so for instance, given a theory of a type theory, given a theory of a T and a model of T, then using this adjunction, I can define a model of this theory in this model as a morphism from the syntactic model to this model, for instance. But I don't know it is in, but I don't know if it is interesting.
Well, I mean, the person asking the question in the chat can clarify with the answers, but okay. Any other questions, comments?
Yeah, I can ask a question.
Yeah.
So thank you for your talk. One of the things I tried to do in my PhD thesis a couple of years ago was construct syntactic natural models, and I stopped short of actually doing that. And it seems like you've pretty much done it. But there's a couple of things that I want to clarify there. And the first one is every model of type theory, in your sense, a natural model equipped with extra structure, or is it something more general?
It's more, I guess it's more general.
So it seems like every category with representable maps seems to have this D from E to U that somehow tells you about types and terms.
Yeah.
So does that give you the representable map in the definition of a natural model?
Yeah. So if a type theory has a kind of generating representable map, then the model of such a type theory should be a natural model with certain structures.
Okay.
But I can define or even more crazy type theories. I don't know good examples, but
sure. And I guess my other question is, so you've defined a type theory to be a small category with representable maps.
Yes.
If I just gave you a purely syntactic list of axioms for a type theory, do you have a systematic way of translating that into a category with representable maps? And I guess from that, like, can you explicitly describe the syntactic model of that type theory? So yeah, I guess my question is, if I just wrote down a bunch of rules of inference on a piece of paper that would conventionally be what someone would call a type theory, would you be able to use the stuff that you've done to show me exactly what the syntactic model should look like? Or is it purely a categorical construction?
Yeah, so yeah, my construction of the syntactic model is purely category theoretic.
Okay.
But at the same time, there is a way to present a category with representative maps using a kind of logical framework. And if we define some type theory, let me see. Yeah, if we get a signature in such a logical framework, we can generate a category with representative maps as a syntactic category in the of the logical framework. What did I say? Anyway, there is a way to present a type theory syntactically using logical framework. But it's not straightforward to such a logical framework. Encoding is a kind of adequate with respect to the inference rules you have in mind.
Sure.
But it's generally is I don't know, correct type theory with I don't know. Yeah, but this logical framework actually generates a correct type theory with a correct notion of a model.
Thanks.
All right, I think we should be wrapping up so that we still have some energy. Okay, so please join me in thanking Taichi again for the talk. And at that point, I think we can pause